All right, now this lesson is going to finish up gas laws, and it's really just going back and looking at the underlying theories behind how gas particles move. Because we've been doing a lot of math in this unit, and those mathematical ideas have a theory behind them called kinetic molecular theory. So we're going to explore that today. Because if you think about it, when you're talking about Boyle's law or the combined gas law or the ideal gas law, those are all laws. They're just basic sort of modeling of observed gas behaviors. They don't actually explain what's going on. A theory is more like an explanation. Like earlier we talked about how pressure is created by collisions with the walls. That's an explanation, right? And kinetic molecular theory is going to sort of wrap up all of those explanations in one nice, neat package. The other thing we're going to do is we're going to look at, well, we've been calling these gases ideal gases, and we're going to get to, well, what is an ideal gas, and therefore, what isn't an ideal gas? And then lastly, we're going to look at Maxwell-Boltzmann distribution graphs to kind of get a feeling for particle velocity and what they can be expressed in those kind of graphs. Okay, so let's look at kinetic molecular theory. Definitely this is a place you want to get your notes out, because kinetic molecular theory, while it's simple, it has some specific principles. There are a lot of things that are true about atoms and molecules that are not sort of captured in kinetic molecular theory. For instance, you may say, do atoms have electrons? The answer is yes, but that's not in kinetic molecular theory. So these ideas are really important ideas and you need to know them. So let's start with one. I don't think any of them will surprise you, but let's start with one. We assume that gas molecules move in straight lines. If you look at the particles in this representation, I think they wrap that up pretty well. Between the collisions, they're moving in straight lines. Seems reasonable. Now, if they collide, of course, they change direction. But without a collision, they will keep going in straight lines. Number two, they don't lose energy if they collide. In other words, they're elastic collisions. Now, you know what that means. If you have two cars that collide with each other, sadly, they don't have elastic collisions. They crumple and stick together. We're assuming they completely bounce back here. It's one of the physics ideas that's underpinning this math. The third one's a little tricky to get to, but there are a number of people who have been working on gas laws who have essentially come to this conclusion on their own, or at least this idea has come into their consciousness. We assume that gas particles have no volume at all in any way. And what we mean by that is if we were to look at this box, let me get a pointer here. If we were to look at this box, let's say that this box is a 3-liter box. Well, you notice we'd use 3 liters in all of our mathematical calculations. But some people have said to me, wait a minute, if I'm calculating a pressure or something about the blue gas and I have the red one in there, doesn't the red one take up a little bit of space? And the answer is, in real life, yes. But one of the ideas behind kinetic molecular theory is that the particles do not themselves take up any room. So you can always use the whole volume of the box. It's as if you scoop them all down to the corner, they wouldn't take up any room in the corner. Okay? So that's one quick, that's the third tenet of kinetic molecular theory. All right, the fourth one, which is a super important one, and is what we're going to be spending all of our time on in the next unit, is we're making an assumption that these particles do not attract or repel each other in any way. In other words, you know how if a asteroid goes by the sun or the earth or anything that has a gravitational pull, it'll sort of bend? That's because it's attracted due to gravity, and we're assuming that these gas particles are not attracted to each other in any way. They're bouncing off each other, but they don't curve as they go by because they're attracted because of a charge or gravitational force or anything like that. All right, now there is a fifth one, but before we go on to the fifth one, I want to say this very important thing. None of these principles are actually true. They all are inaccurate. But we're going to show you in the next slide why we use them. And it turns out it's because it doesn't affect the math much. But there is a way to adjust the math if you find that any one of these untrue statements is a problem. All right, let's look at the last one before we go on to that. So the last one you already know, that the average kinetic energy of gas particles is very much correlated with the temperature on the Kelvin scale, right? Remember, if you double the temperature on the Kelvin scale, the particles on average will go twice as fast. That's not true on the Celsius scale, but it is true on the Kelvin scale. Okay, so gases that adhere to these rules are referred to as ideal gases. That's why it's the ideal gas law, because we're assuming they all obey these particular set of principles. Now, of course, there are no truly ideal gases. None of them. If you look at hydrogen, methane, nitrogen, oxygen, none of them adhere to those principles. And it's because they do have a lot of those, they violate a lot of those ideas. They're real gases. They do have attractions between molecules. They do have size and therefore volume. I mean, they may be small, and the problem is smaller for hydrogen than it is for, like, say, nitrogen, which is just a larger molecule, but they all have this problem. Now, if we were to look at these issues and say, okay, well, hold on, maybe it isn't such a big problem. Like, if I do the math, let's assume I have 1 mole of stuff. I'm at STP, so 1 ATM and 273 Kelvin. And I plug all that in and solve for the volume of the gas. Well, it turns out the answer I should get is 22.4 liters. 1 mole of gas at STP takes up 22.4 liters. If it's an ideal gas. Now, if you do the same thing with chlorine, you take 1 mole of chlorine at 273 and 1 ATM, and you do that number and you calculate it out, it should be 22.4, but if you actually go in and measure the volume, it's 22.06. The math isn't quite right. And if you look at these others that have been calculated, you see it's really close to 22.4, but it's giving you a feeling for how much error we're introducing by pretending like real gases are ideal gases. Now, it's not a lot, but it is there. And you might wonder, well, why does it look like hydrogen is much closer to ideal than, say, for instance, chlorine? Well, it has to do with some of those things we just learned about. Remember, we said gases have no volume. Well, hydrogen is a much smaller molecule than chlorine is, and therefore chlorine really does have volume, and it behaves like it has volume, and so the math is a little bit further off for chlorine. You might wonder why some of these others, you come in here and you look at CO2, it's pretty far off. You may look at chlorine and say, why is it pretty far off? They have to do with these gases have pretty strong attractions to each other, and so they deviate greatly from ideal behavior. So deviating from ideal behavior happens a lot, mostly because of the attractions between between molecules, and those are called intermolecular forces. Now, the next unit we're about to do is all about those forces. We're going to be looking at what causes these gases to not behave in an ideal manner. And there are a lot of different names for these forces. They behave in different ways, so it's not just one attraction. But there are times when real gases, which is all gases, behave better, they behave more ideally. And there are times when they behave very poorly. And you can imagine when those times are. Like, for instance, if you had the gas under very high pressure, and what that means is you have a lot of particles in here. Remember, one of the reasons we can get away with pretending like they won't have attractions for each other is because the truth is the gases are spread out very far. Right? If the particles are spread out very far, they won't see each other very often. Right? It's kind of like if you're supposed to go straight to class and you don't see any of your friends along the way, you're more likely to go straight to class. You are not attracted to that person you see in the hallway. But if the hallways are really crowded and you're walking down there, you may say, hey, there's somebody I know, and you kind of deviate and turn over and see how they're doing, right? You don't go straight to class. So if you're under high pressure, then if there are a lot of students around, you're more likely to see those friendships and interact with people. There's one other situation where real gases behave poorly, other than under high pressure where there's lots of particles. And that turns out to be as if those gases are very cold. If they're very cold, they're moving slowly. Now you see these are moving pretty fast, so you can imagine if you're like running to class and you see that special someone, you're like, I don't have time, I gotta keep going. But if you are moving very slowly, you're kind of, lollygagging, you're like more likely to have the time to think, I want to stop and see how you're doing. And the same is true for gases. If they have so much kinetic energy when they're going by, those weak attractive forces aren't going to play much of a role. But if they're floating very slowly, imagine an asteroid going very slowly by the Earth, it's going to get caught into that gravitational field. So if they're under high pressure, there's lots of them. they're going to deviate from ideal behavior. And if they're very cold, they're going to deviate as well. All right, now let's look at how we can express how fast particles are going. I don't know where to, I may have to just turn me off. But in any case, these are called Maxwell-Boltzmann distributions. And what they get at is when we say that particles go faster the higher the temperature, that is true, but that's only on average. Like, look, if you look at these, if you stop and stare, do you guys see that one? Ooh, occasionally you'll see one that's like barely moving. And you'll see some moving much faster than the others if you look really closely. So when we say if you double the temperature on the Kelvin scale, they will go twice as fast, we're only talking about the average speed. We're talking about, like, you know, here's the average speed. This peak is going to go up a little bit further down on the speed scale if you jack up the temperature. So what a Maxwell-Boltzmann distribution is showing you is you see on the side really small, it says number of molecules. It's just a count. If you were to, you know, calculate the area under the curve, which if you're in calculus, you know how to do that, right? Integration, right? You're doing a little integration. You can figure out what the area is, and it should relate to the number of particles. Well, if you increase the temperature, the average temperature will go up. Will there still be some that have a speed of 0? Yeah. Will there still be some that are going much faster? Yes. But watch what happens if you increase the temperature. Yes, the average, the peak goes further and further down, but it's also getting shorter. And if you're a person who's done a little bit of calculus, you realize, well, or, you know, just math in general, if the area under the curve represents how many particles there are, well, this area under the curve cannot change. It has to be the same. And as you get going, getting hotter, even though the average temperature or kinetic energy is getting higher, and many are going way faster, there are still some that are moving slower, so that peak sort of spreads out a little bit. And because it spreads out, it has to come down a little bit shorter to keep the number of molecules underneath the area there constant. So Maxwell-Boltzmann distributions are really simple. They're just meant to express this idea that if you warm a gas up, the average kinetic energy gets higher, but the difference in their speeds becomes wider and wider. Some are going slow, and some are going pretty fast. All right, so the area under that curve must be constant because it refers to the number of particles in that gas. So the average velocity of the gas particles increases with temperature, but you still have a variety of speeds, right? Seems to make sense. The distribution of velocities increases with increasing temp. So they spread out, some are going faster, some are going slower. Now there's one other thing before we wrap up. We're almost done with this lesson, but there's one other thing we've got to talk about before we wrap up. Yes, temperature does directly relate to kinetic energy, but it doesn't directly relate to velocity. Now I want you to think about why. You may have, if you've ever taken a physics class, even in middle school, a lot of times people learn kinetic energy is equal to 1/2 mass times velocity squared. Well, if you have a particle that has the same kinetic energy as another one, because like it's in the same container, it has the same temperature, you might think, is it moving the same speed on average? And the answer is no. They have the same kinetic energy, but they aren't moving the same speed. Think about this. A truck going 30 miles per hour that runs into a vehicle may do just as much damage as a sports car doing 80 miles an hour. Because we're talking about how much energy they contain, not necessarily how fast they're going. So if two particles have the same kinetic energy, if one is much, much more massive, its velocity will have to be slower. The big molecules will be moving slower if they're at the same kinetic energy. And the small molecules will be moving faster. You like how I expressed that? It's pretty cool, huh? So that's super important to understand. So if we're talking hydrogen, if hydrogen has the same kinetic energy as chlorine, well, chlorine's going to be moving a lot slower because it's a much, much, much larger molecule. Hydrogen's so small, it's going to be moving really, really fast. Okay, now there was a time when we used to actually calculate these speeds, and if you're wondering what the difference is, it's pretty significant. You know, these things are moving hundreds of meters per second. But at this point in AP, they've decided that we're not going to actually calculate that. So if you're super interested, you should ask me. But this is the important idea, that if two particles are in the same container, they must have the same temperature, they must have the same kinetic energy, but that does not mean they're moving the same speed, because the heavier ones will be moving on average slower than the light ones. All right, great job. That finishes up our unit. And we'll be moving on to intermolecular forces next to find out about these attractive forces that we've been ignoring all unit.